Okay, so welcome everybody to this Thursday talk. Today we have the pleasure to have with us, not physically, but virtually, Lorenzo Calibbi from China. Lorenzo is an expert on flavor physics, and today he's speaking about flavor-violating decays on leptons into Axion-like particles. If you have any questions, just interrupt me. Lorenzo will be happy to answer. So please, Lorenzo, it's yours.
Thank you. Good afternoon, everyone. Thanks, Luca, for the invitation. Thank you all for having me there virtually. Of course, I would prefer to be in Madrid. Hopefully, that will be possible soon. I'm going to talk about a quite long paper written in collaboration with these three friends. And as Luca mentioned, I will be happy to be interrupted and have a lively discussion if you have any questions during the talk. Just let me know if some point the connection becomes bad and you don't hear me anymore. I will try to fix it. Okay, so I don't think I have to explain to this audience why we are looking for lepton flavor violation in the charged sector. The reason is simply that we know already that the lepton family numbers are not good quantum numbers. They're not conserved because of neutrino, because we observe the neutrino oscillations. And we know that in principle, this gives rise to lepton flavor violation in the charged sector too. This Fedon's diagram transmits in a sense, the flavor violation from neutrinos to the charged leptons, but the effects are phenomenologically negligible. But the point is, it's not because lepton family numbers are approximately conserved. Actually, we know that the PMNS mixing angles are large, so the lepton family numbers are actually broken to large extent. So the suppression is more an accident of a separation of scales. The fact that neutrino masses are so much lighter than the electroweak scale. So this ratio to the false power makes the processes like mu2 gamma and so on virtually unobservable. Which also means that if we discover them, they're a fantastic, clean, and unambiguous sign for new physics. And the fact that the violation of the leptonic flavor is large and the suppression is perhaps accidental, as I was mentioning, also motivates us to see whatever new physics may be at the TV scale or even at 10 or 100 TV coupling to leptons in a not trivial way. What does it predict for lepton flavor violating observables? Well, classical example, as you know, is supersymmetry. If you substitute to these particles in the loop the supersymmetric partners, there is no reason why this diagram should be suppressed. In fact, from the present bounds of mu2 gamma, a generic flavor structure of the supersymmetric particles, if you had order 1 mixing angles here, this would be excluded already up to 100 of TV or something like this. So this also showed that these processes are a very stringent test for any new physics that couple to leptons, unless you have some protection, some flavor alignment or mechanisms of the kind. And of course, you can probe scales that are way beyond the scales that we can directly test at colliders. And the good thing is that we have experiments and we have been searching for processes of this kind, mu2 gamma, mu2 mu2 conversion in nuclei, the corresponding process in the tau sector for many years. And there are a number of experiments that are being built now or planned, and that will increase these limits by several orders of magnitude in certain cases in the upcoming years. So we have experiments, and it's a good thing to keep looking for these very clean signals for new physics. But what I'm going to focus more in this talk is another kind of lepton-flavour-violation, in a sense, more exotic, or at least less studied than mu2 gamma, mu2 conversion in nuclei, and so on. So the question is, what if the main decay mode that violates the leptonic flavor in the charge sector is not one of those that have been searched for so many years and with such a high sensitivity? So the assumption here is that we have some light new physics. Light new physics in the form of a new light particle, which is invisible for the point of view of our particle physics detector. But it couples in a flavor violating way, so to leptons of different flavors. So light means, in this context, of course, lighter than the muons and the taus. And invisible requires that it is electrically neutral and long-lived, or at least long-lived enough to escape a detector. So which means that does not couple to the standard model particles strong enough to decay promptly. So something with weak, very weak couplings, neutral, lighter than the muon and the tau. So you see, if indeed it couples to a muon and an electron, or a tau and a muon and so on, then the leading flavor violating decay modes of muons and taus would be rather something like this. So a two-body decay into a lighter lepton and this invisible particle. So from the point of view of the experiment, just missing energy. Two-body decays, possibly also three-body decays if a photon is radiated, and so on. So under this assumption, there is also the possibility of playing a comparison, so interesting interplay with constraints of a completely different nature. So not from ground-based experiments, but from astrophysics and cosmology. Because of course, if it is very long-lived, this object could be in principle a dark matter candidate. And if it is light enough, and if it is feebly coupled enough, it is also subject to quite stringent constraints from astrophysical systems, like star cooling and supernova explosion, as I will mention later. So there is this interesting interplay too. So the most perhaps natural setup to study such a kind of phenomenology is in the context of a pseudo-Nambu-Goldstone boson. So this would explain naturally why this object is light and why its couplings to the standard model are suppressed. So if we have some global U1 that is spontaneously broken, then of course we will have a Nambu-Goldstone boson, pseudo-Nambu-Goldstone boson, if you if it is massive, because a small explicit breaking of the symmetry, which could be done by some non-perturbative physics like anomalies and so on, like the case of the Axion. So what I'm going to focus is indeed this class of models that people also dub as Axion-like particles. But in fact, I mean, there may be many examples of symmetries, broken global symmetries that we know or we introduce to do something else, like family symmetries to explain the flavor hierarchies, Peche-Quinn in the case of the strong CP problem, and so on. So the pseudo-Nambu-Gosson boson then would take different names. But from the point of view of its couplings to fermions, and in particular to standard model leptons, independent of what is the specific origin of the UV completion of the model, for the whole class of models of this kind, the coupling would look like this. So what you have here is the classical coupling, derivative coupling of our light pseudoscalar to a vector and an axial vector, leptonic current. I like to write it in this way because the derivative coupling makes it apparent that this is a pseudo-Nambu-Gosson boson. So it has a shift symmetry. So an object with no potential to start with. And as I was mentioning before, the mass comes from some perhaps small explicit breaking of the symmetry. And these are, of course, dimension 5 operators. So the couplings are suppressed by a scale that can be very large, and it is associated to the vacuum expectation value of the field that spontaneously break the symmetry. So the couplings are naturally suppressed if this scale is large. And as you can see here, I am also writing some dimensionless coefficients which are actually allow them to a particle to couple in principle. So we may wonder if this is an ad hoc assumption, but actually towards the end of the talk, I will show a couple of explicit examples. It's quite generic in a quite broad class of models that indeed these couplings are not flavor conserving, not flavor diagonals. For instance, it's unavoidable in case the U1 charges of the standard model leptons are flavor non-universal, are different for different flavors. In that case, flavor-violating couplings are automatic. Or it may be also that they are, on the contrary, the same for the 3 generations, but still loop effects can induce the flavor-violating couplings. But for the moment, I will just focus on this Lagrangian. So just from a phenomenological point of view, without asking myself where these couplings come from. So it's a Raider model independent approach. And so you see, from a Lagrangian of this kind, generically, you have the decays that I was showing before. So a 2-body lepton-flavour-violating decay. A lepton to a lighter lepton and a light invisible Axion-like particle. Here you see the decay rate, of course, scales like 1/f². Here I'm just redefining this scale together with the coefficients. So I'm reabsorbing the coefficients in a number of, let's call it, flavor-violating effective scales. Okay. So the idea here is, first of all, to try to understand which experiment tell us something about these parameters, this scale. So how can we constrain, looking for these decays, these flavor-violating scales? So which experiments we had in the past, and what are the future prospects to place better constraints, more stringent constraints on this kind of processes. So my goal is to show a plot of this kind. I will do at the end, but I anticipate it. So you see, it's a very busy plot. There are several ingredients. Some constraints come from muon decays, others, fewer from tau decays, and there is also the astrophysical constraints that I was mentioning before. Here, well, the goal of the talk is basically explain how we made this summary plot. Here, I'm just anticipating that I'm putting constraint on a plane where we have the mass of the axion-like particle here, so that we treat as a 3-parameter, and the U1 breaking scale. So if you want, or if you want the ALP decay constant, anyway, the scale FA here on the y-axis. And as you can see, these present bounds, which are these thicker lines, make already up to 10 to the 9 GeV or more this scale. And the future bounds, so this thinner line, could go even beyond 10 to the 10. So you see already that this is a striking difference with respect to, let's call it the standard lepton-flavour-violating processes, mu2 gamma, mu2 3, which can test quite high energy scales, but not more than 10 to the 7 or perhaps 10 to the 8 GeV in the future. And the reason is simply because these processes are induced by dimension 6 operators. So they scale like the 4th power, one of the new physics scales to the 4th power. While these are dimension 5 operators, so the scaling, as we've shown, is just 1 over f squared. So if you have something very light, actually you can indeed test, let's call them new physics scales. Well, anyway, it's a scale where something is happening, a spontaneous breaking, so then there will be also UV completion and so on, which are quite large than the typical new physics scales that we can probe even in these very high intensity searches for Fourier processes. So are in fact among the largest scales that we can test in a ground-based experiment. Okay, so let's talk about the experiments first. So the signal, now I will be mostly focusing on muons. So the signal, of course, is just a monochromatic electron, or more often positron, since this experiment typically employ mu plus. So a monochromatic positron, well, if the axion-like particle is almost massless, of course it is around half of the mass of the muon. Otherwise, it will be somewhere else on the usual muon decay spectrum. And if you write the differential decay rate, you see that there is a term that depends on as an angular dependence, and depends on the chirality structure of the couplings. So whether it couples to a vectorial current or an axial current or both, or in which way. Well, and this is actually exactly what happens in the standard model too. So if you take the so-called Michel spectrum, which is nothing but the differential decay rate of the standard muon decay to electron neutrinos, we also have this anisotropy which depends, like in this case, on the polarization of the muon, and on the angle, which is in fact the angle between the direction of emission of the positron and the polarization of the muon. Okay. While this x is just the momentum of the positron normalized by the muon mass half. So it would be 1 at the kinematical endpoint of the Michel spectrum. So the interesting thing is that these experiments, like the experiments performed at PSI, MEG, to look for mu-T gamma, usually employ highly polarized muon beams, just almost for free, because they produce them from pion decays. So hitting a target with protons, they produce pions. They have a large amount of what they call surface pions, which are basically at rest at the surface of the production target. And so these pions then decay into muons, neutrinos. So the muons are very, very much polarized. So you see from here that under certain conditions, you can actually suppress the standard model decay, which is a background, of course, because the signal is similar. It's a positron and invisible things, okay? Simply here we are looking for a line, and here we have a spectrum. But if we are at the kinematical endpoint, so close to x = 1, the muons are polarized. If you look at the forward direction with respect to the direction where the muons comes, and then they get stopped, so the direction of the muon spin, in the forward direction, the Michel spectrum goes to 0 in this way. Okay, just because of this formula. So this then suggests an experimental strategy to look for this. So precisely to look in the forward direction. And this was done already many years ago by this experiment performed in Canada, Triumph, in '86. They were actually testing the Michel spectrum, looking for possible right-handed currents effects in the ordinary muon decay, but they also employed their data set to look for light invisible things. So, well, basically they had a spectrometer with a very good momentum resolution. And, well, when they interpreted their data for research for mu2e invisible, indeed, they were looking for a virtually massless object, so whose signal would be indeed a peak at the kinematical endpoint, where in the forward direction, the highly polarized muon B does not give any positron, or, well, very much suppressed. So they had only 10⁷ muons, okay, but they had a very, as I was mentioning, a very precise experimental setup. So they could set a bound of the level of 10⁻⁶ in the branching ratio. But of course, this bound depends on the actually on the couplings of this object, because you understand if the Axion-like particle couples to a V-A current, so only to left-handed leptons, exactly like the standard model muon decay, then also the signal would be suppressed in the forward direction, exactly in the same way as the background. Okay, so this search then is only sensitive to an Axion-like particle that couples not V-A, only to right-handed, or at least to some extent to right-handed Fermi. Of course, it's maximally sensitive to a V+A current, but also an isotropic decay. So if a coupling to the vector current is a 0, or the coupling to the axion current is 0, then you see the decay is isotropic. So in that case, it's also, of course, this search was also sensitive. So in the case of the isotropic, they interpreted in the case of the isotropic decay, and they set this bound. And then we can, with this caveat that it depends on the coupling, but still, we can translate it to, of course, a bound on the on this scale, okay, on the effective scale of the mu coupling, and you see it's quite large, above 10 to the 9 GeV, as I was mentioning before. Then we had another experiment, same laboratory trial, called the twist. They were also measuring something else, again, the Michel parameters, but they employed the data. In this case, they had well, 1 order of magnitude more muons, or a bit more. And well, they were basically looking for a bump on the emission spectrum. So in this case, they could do a search for axion-like particle, also heavier one, so all the way up to almost the muon mass. And they were less sensitive than to this anisotropy of the signal. So they could also place a bound in the case of axion-like particle that couples B minus A, like the standard model like. So in that case, if the things is quite light, then this is the best bound we have for a V minus A coupling ALP. So you see just something 6 times 10 to the minus 5, which still translates to a quite stringent bound on the scale. But in terms of branching ratio, it's a quite weak bound if you think what the modern experiment sets as a constraint on processes like mu2 gamma, order 10 to the minus 13. Okay. And well, the situation for the taus is even worse in a sense, because the B factories could have searched for this, but they didn't. So the only limit we have dates back to 95 from an experiment at Daisy called Argus. And the limits are just at the per mil level, something in 10 to the minus 3 for tau to E invisible and tau to mu invisible, which can still translate into not negligible constraints on this scale, or that 6B, but still I need to be below the one case coupling with muon, and then this bound.
Lorenzo, I'm sorry, but you're freezing. The voices are freezing at the moment.
There are interesting, but they are all given by either very old or now. Let me try something else.
Now it seems to be better. Try to speak. Lorenzo? Lorenzo? Okay. So let's wait for Lorenzo to reconnect.
Okay, I think, hello, I'm back.
Okay, now.
Sorry about this. Can you hear me now?
Yes, we can. It seems that it's working fine.
Okay. Okay, so sorry, I was just commenting that the bounds at the moment are not very stringent because they were based on not so large sample of muons. because these experiments didn't have a large luminosity, or they were quite old. And so we hope that we can do much better at the next generation experiments. So MEG II, MEG-II at PSI will be working with a beamline that actually can deliver more than 10 to the 8 muons per second. Okay, so in 1 second they will already have the data set of these old experiments. So the prospects must be much better. So our idea is to employ MEG II. Okay, MEG II, you know, is just the upgrade of the MEG experiment that is provided the most stringent limit on a lepton-flavour-violating process, mu3 gamma, 4 times 10 to the minus 13, and they were stopping muons at the target and looking for a back-to-back coincidence of a positron and the photon. And actually they were triggering on the photon. So since they have so many muons, of course, they cannot record any random event. So the data of MEG cannot employ it for our search, okay? Because there is no photon. The signal is actually very similar, but on one side, in our case, is invisible. So we have to see what we can do at MEG II. That is going to start, well, they already did an engineering run, so they may even start to take data by the end of this year. So our idea, our proposal that we put forward in the paper, but it was based with discussion of actually some members of the collaboration, is that we could mimic these old triumph experiments, the one looking in the forward direction, at MEG II. So repurpose or do a dedicated run at MEG II, placing a small calorimeter in the forward direction. So yeah, so since they have a highly polarized beam, they have also magnetic field that can help. They can also help providing something that is called magnetic focusing. So just conveying more positrons in the forward direction, which is something that actually the old experiments did. So our idea is basically to place this 10-centimeter crystal calorimeter in the forward direction about 1.5 meters from the target. And at the end of the main run of MEG II, the one dedicated of mu2 gamma, of course, run like this for a couple of weeks. And the couple of weeks means already collecting order 10 to the 14 muons. And we estimated, of course, it's a crude theorist estimate. This would require some more detailed simulation done with the experimentalists. But from what our estimate, it seems that this could be already enough to improve over the old bounds. I'm not going into the details here, but here I'm plotting what is the limit depending on certain experimental parameters. So the resolution of the momentum resolution of the positron. So in this case would be the momentum resolution of the little calorimeter. Of course, because we want to distinguish a peak at an end point. So the narrower is the peak because we have a better resolution. Of course, the better we can discriminate between signal and background. And then how well we control the polarization. So if we assume that we can have a 1% momentum resolution, a 1% control on the polarization, so we don't have more than, we have 99% polarized muons, then this is our benchmark, and we see that we can already improve over the old limit by a factor of 3 or something like this. And if on top of that we have this magnetic focusing, so which basically increases the geometrical acceptance of our calorimeter, even by a factor of 100. This is what the old experiment achieved. Then we could do much better. We could place a limit which is more than 1 order of magnitude better than the present one, so below 10, around 10 to the minus 7. And then, of course, there is also the other experiment, MEG II. They are going to search for mu-3 electrons. So again, stopping in a target, and then they have this, well, cylindrical shaped detector. So on the surface of the cylinder, they have these tiles, and the 3 electrons, so the positron and the 2 positron and the electron, then would curl around their strong magnetic field and hit these tiles and several times. So this allows them to have a precise reconstruction on the interaction point, if you want, of the point of the stopping target where the muon decayed. The nice thing is that they are recording, well, they can perform an online search in this case. So a member of the collaboration actually published a PhD thesis showing that using the data they have on the positron, that they can obtain online, so they don't trigger, they just field some so-called momentum histograms with a limited number of information, basically just the number of tracks they have at the momentum. So they can handle a larger rate of data. So they could draw this, which is just the Michel spectrum, and look for small bumps on the spectrum. So look for the two-body decay. So for our signal, for a monochromatic positron. So according to this study, then already the phase 1 of the experiment, about 10 to the 15 muons, should be able to improve. This is the old bound from Twist on the branching ratio as a function of the mass of the invisible particle. They could improve even by 3 orders of magnitude or something like this. So again, at the level of 10 to the minus 7 or better. If the object is particularly light, lighter than 30-20 MeV, you see this red line shows a deterioration of the sensitivity because calibration problems. So in practice, these experiments actually use this standard model decay. So the position of the kinematic edge to calibrate the momentum. So if they actually have to search for a peak here at the edge, then they would need to perform calibration and signal search at the same time. So it does introduce systematics. So this is why the sensitivity deteriorates. However, they could think, they propose some alternative calibration techniques. If they manage, then they could improve even by a further order of magnitude, go down to 10 to the minus 8. But anyway, conservatively, they should already be able to do this, which is a very nice improvement, which would translate in a constraint on the scale above 10 to the 10 GeV. And finally, there are, of course, prospects at the B factories, in the sense that, as I said, B factories didn't search for this, but they could. They have the data. So there was a study of some collaborators in Bell who simulated what could be the bound in the case they do the analysis, and they would reach order 10 to the minus 4, more than 1 order of magnitude improvement. Of course, they have like 2,000 more data than that old DAISY experiment. And so if we simply rescale it naively with the square root of the luminosity from Bell to Bell 2, which hopefully will collect 50 inverse afterburn within 1 decade or so, this could really bring to a substantial improvement. So the branching ratio could go down to, the limit could go down to 10 to the minus 5, and the constraint of the scale well above 10 to the 7 GeV. And actually, after we published the paper, we saw also this Bell 2 note where they did a simulation showing that they would already improve on the old bound just with the 25 inverse femtobarn. And as far as I understand, talking to them, well, now they have already 60 or 70 inverse femtobarn, so they're planning probably to publish a real search finally, so not just a simulation, so to do the analysis and publish it sometime, maybe even later this year or at the beginning of next year. So we may have a substantial improvement on this channel soon from Bell 2. Okay, so this is the particle physics part. So let's go more quickly on the astrophysical implications and the cosmological implication of this thing. So first of all, here we were focusing on the coupling, so of a muon of the Axion-like particle to a muon and electron, or to a tau and a muon and so on. But the flavor conserving counterpart of those, in particular the coupling to electron, is very much constrained by astrophysics. The point is that a process like this can occur. So, and just an electron recoiling on nuclei in the stars could emit an axion-like particle. And if this axion-like particle is weakly coupled enough, it behaves like neutrinos. So, like neutrinos would contribute to the cooling of the star, to the energy loss of the star. And this set a quite stringent bound on this effective scale of the coupling to electrons, also order 10 to the 9 GeV from the observation on white dwarfs and red giants. Point is that this is an effective constraint only if the axion-like particle is light enough. Of course, because the star must have enough energy to produce. So if the axion-like particle starts to be heavier than the average temperature inside the star, which for the dwarfs is around a few keV, for the red giants around 10 keV, then this process would be Boltzmann suppressed. Okay. There are even hints for non-standard cooling in white dwarf, apparently, at the order of 3 sigma. Even a new paper appeared today about this. So apparently, yeah, the possibility of the of having something light that escapes the star and cools down, so provides some non-standard energy loss beyond the one due to neutrinos, it would be also welcome if the coupling, so the scale is of this order. So what we did is just taking these known couplings, constraints in the literature and just, yeah, extrapolate them also for heavier axion-like particles, so taking into account this Boltzmann suppression. So we could draw a constraint as a function of the axion-like particle mass that surprisingly was not available in the literature at the time. And one can do a similar game also for the data from the famous, this is a type of 87 supernova, because well, also the neutron star that is forming during the explosion also would cool down too quickly if this process is too effective. So one can set a bound which is weaker than the bound from white dwarfs and red giants, but it extends also to much heavier axion-like particles because the supernova was much hotter. Okay, so you can set a bound up to almost order 100 MeV in this case. So these are the bounds that then we collect from these sources, from these references. And finally, cosmology, dark matter. Well, as I was saying, the first requirement, of course, to be a good candidate of dark matter is that this object, this particle, is long-lived enough. So at least with a lifetime longer than the age of the universe. But then, since it couples to leptons, so it will decay to photons via loop, or even due to an electromagnetic anomaly, like axions, right? It can couple to photons, so it would always decay into two photons. So we have bounds from there, and they are more stringent depending on the UV completion. In particular, if you have an anomalous coupling to photons, these bounds can be more stringent. And these decays into photons could be observed as extragalactic background light, or depending on the mass of the object, they could be observed as X-rays coming from galaxies that are rich in dark matter, and so on. So there are bounds from the light that this thing would emit decaying. But otherwise, if these constraints are fulfilled, then it can be a good dark matter candidate if, of course, you can produce it somehow in the early universe. And you could do it like an ordinary axion through the misalignment mechanism, for instance. So if we take into account the astrophysical and the cosmological constraints, we can obtain a plot of this kind. Here I'm plotting again the two parameters, the scale, the decay constant, and the mass. Here I'm showing also very light objects. So on the left of this region here is long-lived at cosmological scale, so its lifetime is longer than the age of the universe. And this is the bound from extragalactic light. So this region is excluded. If the coupling to photon is suppressed because the U1 charges are not anomalous, so you don't have the anomalous coupling to photon. If you have some anomaly, then this bound becomes much more stringent. So this is model dependent. But otherwise, all in this white region, this thing could be a dark matter candidate. And well, the misalignment mechanism, with some caveats, could even produce it to large extent, 100% on these lines. And the bounds from the stars are this gray region here, so below something 10 to the 9 GeV. So all this region in principle is unconstrained region for axion-like particle dark matter. And it could be even searched for with ordinary axion experiments. So these are the possible future bounds from all the projects that are searching for axions. Here I'm even showing this famous xenon one-ton excess in electron recoils. That, for instance, these people here show that if we have axion-like particle dark matter, so if axion-like particles are present in the halo, indeed could give rise to a signal of that kind if they are of the order of 2, 3 keV with a certain coupling to electron. Small, but not so far from the present bounds. But anyway, below the bounds from stars. So, and we are showing it here. So it's actually in a region that, well, if the coupling to photon is suppressed, is at present unconstrained, and it could be even in the reach of our MEG-II and our MEG II proposals, which is this orange line. Of course, if this axion-like particle couples to μe. Okay, but anyway, this shows that these experiments can test the parameter space of this kind of models beyond the star cooling bounds, while the old experiments were at the same level or below, so they could not really test new physics beyond what we knew already is excluded from astrophysics. And it could even, well, test interesting parameter region where the axion-like particle is a good dark matter candidate. So finally, I can put everything together and show you again this plot. So this shaded region, now we know what they are. They are the region excluded by white dwarf, red giants. As you can see, the limit, the constraints, terminates at some point because of the temperature of the star, as we were saying, while these are supernovae bound that can extend up to 100 MeV, but they are comparatively weaker. Our old bounds are these thick lines. So this is the bound from Argus, from tau decays. So these are the bounds from the old experiments, depending on the chirality of the couplings, on if it is V minus A, V plus A, or isotropic. Okay, and as you can see, yeah, at least for a light axion-like particle, they were not beyond the star bounds, as I was mentioning. While the prospect for the future experiments are well, much better. They can really test new parameter space, so beyond the stars, in principle. The point is that, well, this is what we can do in a model-independent fashion. After this, we need to discuss specific models. The reason is that to show all these constraints on the same plane, although they refer to a couplings to involving taus, or couplings involving muons, or just flavor-conserving couplings to electrons, like the stars, what we did is just put all the coefficients equal, the same, in this case, equal to 1. So this is why I'm directly constraining just this scale F, the VEV that breaks the U1 symmetry. Then, of course, in an explicit model, the relative importance of these constraints will be rescaled, because it may be that some mixing angles suppress the flavor-violating entries of these matrices compared to the flavor-conserving. Okay, so then we have to see in a specific model, especially the flavor structure of the model, how these constraints translate. Okay, so to see if really these future lepton flavor violation experiments can test these ALPs beyond the stars, we need to specify a flavor structure, a specific model. So to know what is the correlation between the flavor conserving and the flavor violating couplings. And also to answer the question that I was mentioning at the beginning, how generic is to have flavor violating couplings of this kind of light particles in the first place. If it is a tuning or a model building exercise, or if something that you obtain quite naturally. And in the paper, we showed 4 explicit examples where this occurs. Here, in the last 10 minutes, I'm just showing 2 of them. One is just a QCD axion. It's really, from the point of view of the CP, strong CP problem of dark matter, is just an ordinary axion model of the DSFZ type. Okay. The only thing we did is that we assumed that leptons of different flavors, electrons, muons, taus, carry different Pechequin charges. Okay, so non-universal Pechequin charges. So that's why we call it lepton-flavour-violating QCD axion. And well, I will show you in a minute. It's very easy to see that if the this charge assignment is lepton non-universal, then lepton-flavour-violating couplings arise. And the other example is the muon. So the pseudo-Nambo-Goston boson of a spontaneously broken lepton number. And we worked on that in the context of low energy system models. So the QCD axion. So I'm not really showing all the details of this model, but just how these couplings are my dimensionless couplings to the vector and axial vector leptonic currents arise in this context. So here there is the usual n number, so basically the QCD anomaly coefficient. And then the couplings of right-handed and left-handed fermions, lepton in particular, depends on these matrices I'm calling X, which are diagonal matrices. On the diagonal, I'm putting the Pechequin charges. So you see that if the matrices are not proportional to the unit matrix, so if these entries on the diagonal are different, then when you rotate this coupling here, so when you rotate your fields to diagonalize the Yukawa coupling, so to go to the basis where the charged lepton are masses are diagonal, are flavor diagonal, so the mass eigenbases, then of course this rotation induce off-diagonal entries. So lepton flavor non-universal charges well, directly imply flavor-violating couplings. And of course, this then depends on what is the flavor structure, or I mean, what are these rotation? And this has nothing to do with our model. It depends on what is the flavor structure in the, if you want, in the interaction basis of the standard model Yukawa couplings to start with. So here we are showing, for instance, if this term dominates, if the rotation of right-handed rotations are large, so then of course you see the axion-like part, the axion, in this case it's a QCD axion, mostly coupled to right-handed lepton, of course. So the coupling is B plus A. Well, otherwise, if you have larger left-handed rotation, now this term dominates, the thing couples mostly to left-handed leptons, and of course the coupling is of the B minus A kind. But then we can plot things similar to any other axion model. So the usual plot of showing the axion searches, mostly based on Primakov effect in the plane of the coupling of the axion to photons versus the mass of the axion, which is related to the inverse of the axion decay constant Fa. So we can show both. And so these blue lines are typical models. Our model would be this orange line. It stops here because, well, stops here because above this this mass, you do not fulfill the white dwarf cooling bound. And this shows that the white dwarf cooling bound is, at the moment, more stringent than the bound from μ2e invisible. And even more in the case of the right-handed, sorry, of the left-handed, of an axion coupling to left-handed currents, precisely because for a V-A axion-like particle, as we have shown, the bound is weaker. But in the future, these are instead is the future bound from MEG II and μ2 in this case only μ2 because MEG II would not be sensitive to a V-A axion-like particle. I was saying in the future, we can go beyond the stars. So this is an explicit example where we can test some new parameter space with these lepton-flavour-violation experiments beyond the star cooling bound, improving by a factor of few, not so bad, the bound, for instance, in terms of the axion mass. Okay, and of course, then there is an interplay with the axion searches, ordinary axion searches, let's call them, and so on. So these are two examples where indeed we found a model that, well, can be tested better by lepton-flavour-violation than by astrophysics. And the second and last example is the muon. So this can arise in the context of the standard type 1 seesaw. We know in the type 1 seesaw what breaks the lepton number is the mass of the heavy Majorana neutrinos, of the right-handed neutrinos. In our case, we promote this to, well, we break the lepton number spontaneously. So instead, we generate these mass terms through the web of a new scalar field, sigma. So the mass of the right-handed neutrinos will be given by the web of this new scalar field times this matrix of couplings. And as usual, you see, we can write this field. We can show the web, the radial excitation, if you wanted, the real part of it, which will be a heavy X. And as a phase, no, the pseudo-number custom boson. So traditionally, they call it the J for some reason. So this J is precisely our muon, our pseudo-number custom boson. And due to this coupling, yeah.
Lorenzo, just let me tell you that you are running out of the time.
Yeah, sure. Yeah. I just missed one or two slides. Okay, thank you. So it couples to right-handed neutrinos. But since in the seesaw mechanism, right-handed neutrinos mix to some extent with left-handed neutrinos, then through loops, it can couple to gauge bosons. So this kind of coupling to Z then would induce a coupling of the muon to leptons, but also quarks. But it's flavor conserving because it comes from the standard Z coupling. But if you have a coupling to due to this triangle with the W here, now with different PMNS entries, you can couple the muon to leptons of different flavor. So the couplings look like this. They are of the off-diagonal ones, the flavor-violating ones are of the V-A kinds, because they come from a coupling from the W, so they just couple to left-handed leptons. And well, as usual in this lepton-flavor violation, they depends on the Yukawa matrix of the neutrinos. So in the combination of Y dagger. Of course, you know better than me there in Madrid that these, I mean, if this is order 1, then this scale must be very large, 10 to the 15 GeV or so, in order to give the correct light neutrino masses. So if you want large couplings and the lower scale, in order to have visible effects here, you will need to play some trick, maybe inverse seesaw, or other kind of low energy seesaw, for instance, with those pseudo Dirac right-handed neutrinos, 2 pseudo Dirac right-handed neutrinos with approximately conserved generalized lepton numbers, what Alejandro Ibarra with Molinar and Petkov did 10 years ago, something like this. Okay, so you need to work in a setup of low energy seesaw in order to have visible effects, because the bounds that we can place are of this kind. So the future constraint from mu to 3 will reach scales of order to the 10 GeV, which means that, well, Majorana neutrino masses of the order of 10 to the 7 GeV. So we can test up to there, okay? So you need, I mean, to have something visible, to observe this, this process, you need an additional suppression mechanism to explain why the neutrino masses are so light. But in that context, in that class of models, indeed, these plots show that our mu to 3, future bound from mu to 3, will really go beyond the bounds from astrophysics, star cooling and supernova. And there is even a corner where the tau decays can test something that, of course, since when the Majoran is too heavy, neither the stars nor the muon decays can arrive. And this is also a good model for the Xeno one-ton excess, by the way, because the lepton number is anomaly free. So the coupling to photon is suppressed. So here you would fit the anomaly. And the bound from lepton-flavour-violating experiment is not going to be, is going to get quite close to that region in the future, hopefully. Okay, sorry. Since I'm running actually really over time, this is my summary. Well, I hope that I convinced you that this pseudo-Nambu-Goldstone boson that couple to leptons of different flavors are not such a crazy assumption. I mean, they may arise easily in wide classes of models via loop effects or non-universal coupling. And the interesting thing is that we have a really very large room for improvement because the old bounds were old and not so sensitive. So especially with this MEG II proposal of ours and mu to 3, we can really improve over the present constraints in the next few years, in the upcoming years. And there is a nice interplay between different channels, mu and tau, depending on the mass of this Axion-like particle. If it is heavy enough, only the taus can test it. Lighter, of course, the muons tend to win, and then also the astrophysical bounds are relevant. So there is a nice interplay among different observables, and very large scales can be tested. And as I was mentioning, at least for the examples that we studied, we saw that these future experiments can test these models even beyond the astrophysical bounds and start probing a region where very interestingly the Axion-like particle can be dark matter. Okay, I will stop here.
Okay,
Thank you
thanks a
for
lot.
your attention.
Thanks a lot, Lorenzo. It's time for questions from home or from here for the audience. If there is any question from Zoom, please just unmute yourself and speak loudly. In the meantime, if there is any question here. So one of the questions that I can do in the final plot that you were showing in slide 38.
This one?
Yeah, that one. So essentially, this is made under the assumption that these ALPs are very, very light, either axions or just Gospel boson that are very light. If you consider them pretty massive, for example, 1 GeV, that is one of the masses that has been taken for ALPs, how difficult is to extend your analysis considering visible decays? So would it be possible in MEG II doing something with visible decays?
Okay, so well, you see here, basically, I'm just plotting up to the tau mass, of course, because I mean, so actually up to 1 GeV, more or less, because I'm interested in the decays of the leptons into this particle. Okay, so one thing I could not discuss is that, of course, the visible decays you mentioned are relevant, but not for this parameter space that I'm showing. Okay, the point is that here the object is always long-lived, so it leaves the detector. But you see here I stop at 10 to the 5 GeV in the decay constant, in the suppression scale. If I were to plot lower for lower scales, well, at some points I get also a lower bound in the sense that, well, I lose a sensitivity with these searches because the thing is not invisible anymore. It decays displaced or prompt inside the detector. And even the astrophysical bounds disappear because the Axion-like particle starts being strongly coupled enough that does not escape the star, remains trapped in the star because it keeps interacting with whatever is inside the star, with the electrons. Okay, so it does not contribute to the cooling. So the bounds disappears. So if you go down here, down to scales of 10 to the 3 or maybe 10 to the 4 GeV, let's say TV 10 to the TV scale there, then, well, these models have a completely different phenomenology and what you were mentioning. So the Axion-like particle will decay to 2 photons, or depending on the model, to E plus E minus. So searches for mu2-3, I mean, at mu2-3 experiment will be sensitive to it. Another nice mode would be mu2E gamma gamma, for instance. That maybe MEG II could, well, I'm not sure. Probably still mu2-3 could have a sensitivity to it. MEG II, I'm not sure it's going to search for it. Anyway, yes, so prompt or displaced decays of the Axion-like particle, that point will be relevant. And of course, the heavier it is, the more relevant they are, because, I mean, the heavier, the faster it will decay. For instance, here in this plot, under this certain assumption, I'm already excluding a region where you see I'm writing that the decay length is below 1 meter. So in this corner, most likely Argus anyway was not sensitive because it's difficult to conceive a model where indeed the thing is invisible, long-lived. So here for sure is it decays displaced or prompt.
Maybe it's reasonable to think that these massive ALPs would be better tested in Bell 2 with B decays with respect to MEG on leptons decays.
Well, for sure, MEG cannot do anything if the ALP is heavier than the muon mass. So above 100 MeV, it's just a corner for tau decays if the thing coupled to taus. Beyond that, you're right. Then there is, well, mesons and B physics and whatever else we can imagine. So Bell 2, of course, from B decays, perhaps even J psi or epsilon decays at charm factories or again at B factories and so on. Maybe, of course, a better test. I mean, the leptons for sure won't be sensitive to this too much if it is above 1 GeV. Okay. Of course, I mean, even if it is few GeV, and quite strongly coupled, okay, it may mediate tau to 3 muon or mu to 3 with a virtual exchange, no? With the off-shell axion-like particle. Then you pay the price of the phase space, and it will be suppressed. Anyway, these are the kind of searches that were actually discussed by several papers last year. I have even a slide like, oh, sorry, I lost my slides. Bauer et al., Andrea Tan, and so on, Neubert, right? Paride, Paradisi, and Cornella. So here they were looking for lepton-flavour-violating ALPs. So you see here this plot extends to 10 GeV. And when they are very light, they only have our kind of constraints. In the intermediate region, mu to 3, mu to gamma, gamma, even mu to gamma, just via ALP loop and so on. But the bounds, especially if you write it in terms of the scale, are not very strong in this region here. You see, this is 1 over f is order 10 to the minus 2 TV to the minus 1. So you don't reach very large scale. So really, I mean, these are models that either leave below my plot, where possibly you can try also to play the G minus 2 of the muon with the axion-like particle, or as you said, in the region where they are substantially heavier, above 1 GeV or even 10 GeV.
I see. Okay, thank you. There are questions or the comments? Otherwise, it is already more than 1 hour that we are here, so I think that we can close. Yeah. Okay. I don't think that there are other questions or comments. So thanks a lot, Lorenzo.
Thanks to you all.
And let's hope to have you present physically here maybe next year.
Yes, let's hope so. A nice day to everyone, and hopefully see you soon.
Thank you. Thanks a lot again.
Bye-bye.
Bye.
Bye-bye.